40,000 stone columns march into the sea like a forgotten pathway. This is the giant's Causeway, a landscape so strange it seems born from legend. We are about to uncover the true story of its creation, a secret locked in stone for millions of years. You will learn the precise natural forces that sculpted this wonder, solving a mystery that baffled scientists for centuries. Was it the fury of a volcano or the strength of a giant that built this bridge? What does this ancient place make you wonder about our planet's hidden power? This perfect geometry was not crafted by human hands. It sprawls across the coastline of County Antrim in Northern Ireland, a sprawling pavement of roughly 40,000 stone pillars. Most of these columns lock together in a stunning honeycomb of hexagons, their forms so precise they appear to be the work of a master stonemason. Yet this is a purely natural phenomenon, a puzzle that has drawn inquisitive minds for hundreds of years. Artists have tried to capture its strange beauty, tourists walk in awe across its stepping stones, and scientists have stood here utterly perplexed. How could the chaotic forces of nature produce something of such mathematical regularity? The Causeway does not look like a random rock formation. It looks like a blueprint, a piece of architecture from a time before history. Long before science offered its own explanation, the people of Ireland had a far more thrilling answer for the Causeway's origin. It was not a geological process, but the work of a giant. The legend tells of Finn McCool, a colossal figure of immense strength and occasional folly, who lived on this very coast. His greatest rival was a Scottish giant named Benandana, who lived across the sea. The two would shout insults and challenges at each other over the water, but the churning sea between them made a proper fight impossible. Frustrated, the mighty Finn McCool tore up chunks of the Antrim coastline and thrust them into the ocean, crafting a sturdy causeway of stone pillars all the way to Scotland. This was his bridge, his personal dueling ground, so he could finally confront his noisy adversary. This story was passed down through countless generations, a fireside tale that gave a name and a purpose to the impossible stone pathway. For centuries, it was the only truth people needed. The sheer scale of the Causeway demanded a creator of equal magnitude, and the legend of Finn McCool provided exactly that. It rooted the wonder in the cultural identity of the land, transforming a cold, hard mystery into a warm, human drama of pride, rivalry, and epic strength. The stones were not just stones, they were the deliberate work of a giant, a testament to a time when the world was wilder and more magical. What does this tell us about how people make sense of the world? When faced with something beyond comprehension, we instinctively weave a story around it. We give it a hero, a villain, and a motive. The legend was more than just a fanciful tale. It was a framework for understanding, a way to make the intimidating beauty of the natural world feel familiar and alive with meaning. But legends cannot satisfy a curious mind forever. By the late 17th century, a new wave of thinkers arrived at the Causeway, armed with notebooks and a growing belief in rational inquiry. They were the pioneers of modern science, and the giant's Causeway presented them with a riddle that defied all existing categories. One of the first to formally document the site was Sir Richard Bulkeley of Trinity College, Dublin. He walked among the columns in 1693, his mind reeling at the spectacle. He sent a detailed account to the prestigious Royal Society in London, a letter that sparked a fierce and confused debate among the greatest intellects of the age. The central question was deceptively simple. What were we actually looking at? The stones did not fit any known model. Some argued passionately that the Causeway was a colossal artificial structure, the remnants of a lost civilization whose engineering skills surpassed their own. The sheer uniformity of the hexagons seemed to suggest intelligent design. Others proposed it was a vast fossil, perhaps a petrified coral reef from a time when the ocean covered this land. A third, more exotic theory claimed the pillars were not rock at all, but giant natural crystals that had grown from the Earth. Each of these theories was a desperate attempt to fit the Causeway into a box it would not fit. The idea of a man-made structure spoke to the human tendency to see our own handiwork in nature's marvels. The coral reef theory reflected the limited understanding of deep time and geology. And the crystal formation hypothesis revealed a fascination with minerals and their geometric shapes. For decades, the debate raged without a clear winner. The scientific community was stuck, staring at the same stones as the locals but seeing a completely different kind of mystery. The legend of Fingal offered a complete, if fanciful, story. Science, in its infancy, could offer only competing fragments of the truth. This intellectual struggle highlights a pivotal moment in history, a time when the world was slowly being stripped of its myths and forced to reveal its actual mechanical secrets. The Causeway was not giving up its true origin easily. It would take a new way of seeing the world, a revolutionary idea about the very nature of the planet, to finally crack the case. What fundamental force could possibly create such order from chaos? The scientific debate finally found its footing when researchers looked past the stone itself and into its very essence. They identified the columns as basalt, a rock born from fire. This was the pivotal clue, the undeniable signature of a volcanic past. The Giant's Causeway was not a coral reef or a set of crystals. It was the frozen remnant of a cataclysm. This dramatic shift in understanding pointed to a specific chapter in Earth's deep history, the Paleogene period, some 50 to 60 million years ago. At that time, this now tranquil coastline was a shattered wound in the planet's crust. Fissures miles long tore open, and the land was not a solid thing but a liquid nightmare. From these colossal vents, unimaginable quantities of molten rock called lava flooded the landscape. This was not the dramatic, mountain-building eruption we might picture today. This was a quieter, more profound kind of violence, a slow bleeding of the Earth's interior that blanketed the region in a deep, searing lake of liquid stone. But simply having lava was not enough to create the Causeway. The mystery of the perfect columns was not in the eruption itself, but in what happened next. The true magic, the geometric secret, lay in the slow and patient process of cooling. How does a formless sea of fire become a field of perfect hexagons? The answer is a story written in the language of heat, contraction, and the fundamental rules that govern our universe. That deep lake of lava held its heat for a very long time. The key to the Causeway's geometry was not a rapid chill, but an incredibly patient one. Picture a vast black lake of liquid rock, perhaps 100 feet deep, sitting under a cool, ancient sky. It did not freeze solid in a day or a year. It cooled over centuries, losing its immense heat from the top down and from the edges inward. This slow, steady cooling was the master sculptor at work. As the lava lost its heat, it also lost its volume. The rock began to contract, to shrink inward, creating immense internal stress. Think of a vast, deep puddle of thick mud under a hot sun. As the water evaporates, the mud shrinks and pulls apart, creating a network of cracks. The same fundamental principle was at work here, but on a monumental scale and with a far more dramatic result. This process is known as thermal contraction, a physical law as reliable as gravity. When most materials cool down, they get smaller, but in a uniform mass, this shrinking cannot happen randomly. The stress has to find a way to release itself, and it does so by cracking. The cracks began at the coolest points, the surface and the edges, and then reached down into the still cooling mass below. They did not form haphazardly. The stress distributed itself with mathematical efficiency, seeking the most economical way to relieve the pressure. This is why the cracks met each other at precise angles, forming a network of polygons. A hexagon, with its 120-degree angles, is one of the most efficient shapes in nature for distributing stress across a surface, a pattern also seen in the cells of a beehive or the skin of a dragonfly's wing. So as the lava contracted, it fractured into a sprawling honeycomb of cracks that penetrated deep into the heart of the flow. These cracks are what we call joints, and the entire process is known as columnar jointing. The perfect pillars of the Giant's Causeway are not separate stones that were placed together. They are the negative space, the remains of a single, massive lava flow after it cracked itself apart. Each column is a single, solid piece of basalt defined by the fractures around it. The incredible slow cooling is what allowed the cracks to travel so deep and form such long, elegant columns. A quick cooling would have created only a shallow, chaotic crust of rubble, but here time and a steady chill worked in perfect concert, turning a sea of fire into a field of stone geometry. So the Causeway is not a construction but a deconstruction. It is the breathtaking signature of a planet slowly releasing its own pent-up energy, following rules of physics that are as beautiful as they are unbreakable. Not all lava is created equal. The secret to the Causeway's perfection lies in the specific recipe of the molten rock itself. This was not the thick, sticky lava that builds steep cones, but a far more fluid type known as tholeiitic basalt. Its chemical composition was the key, lower in silica than other magmas. Think of silica as the mineral that gives lava its thickness. High silica lava is like cold molasses, it oozes and piles up. But tholeiitic basalt, with its lower silica content, was more like warm engine oil. It was thin, it was runny, and it could flow for incredible distances with ease. This low viscosity meant that when the Earth's crust fractured, this liquid fire did not just burst forth in one spot. It flooded out, spreading across the landscape to form vast, flat, and incredibly deep lava plateaus. The Antrim Plateau, which houses the Giant's Causeway, is a testament to these immense floods. The lava did not pile up, it spread out, creating a uniform, deep lake of liquid stone that was perfectly primed for what came next. This fluidity was essential for the slow cooling process. A thick, frothy lava full of gas bubbles would have cooled unevenly, creating a chaotic, spongy rock full of holes. But this tholeiitic basalt was dense and homogeneous. It settled into a vast, still pool with a consistent composition from top to bottom. There were no major impurities or pockets of gas to disrupt the transfer of heat. As this immense body of rock began to lose its temperature, it did so as a single, unified mass. The heat escaped slowly and steadily from the surface downward, allowing the stress from contraction to build evenly throughout the entire flow. This even cooling is what allowed the fracture patterns to develop with such mathematical precision across such a vast area. The cracks could propagate deep into the flow, tens of meters down, meeting other cracks at perfect 120-degree angles to form the long, elegant columns we see today. Without this specific type of fluid basalt, the cracks would have been shallow and irregular. The Causeway would have been just another lumpy volcanic field. Instead, the unique properties of tholeiitic basalt provided the perfect canvas, and the laws of physics provided the brush, painting a masterpiece of geometric order that would endure for millions of years. So why hexagons? Why is this six-sided shape nature's favorite blueprint for cracking apart? The answer lies in a beautiful piece of mathematical efficiency. As that immense lava flow cooled and contracted, the stress building within it needed to escape. The material had to crack, but it would do so in the way that required the least amount of energy. Think of it like a tiled floor. If you had to cover a large, flat surface with identical shapes that all fit together without any gaps, what are your options? You could use squares, or you could use triangles, or you could use hexagons. Of these three, the hexagon has the greatest area for its perimeter. This might sound technical, but it means something profound. A hexagon encloses more space with less boundary line than either a square or a triangle. For the cooling lava, this geometric fact was everything. The cracks themselves, the boundaries between the columns, represented the spent energy. To create a network of fractures, the system naturally favored the pattern that created the fewest total feet of cracking. A hexagonal grid minimizes the total length of all the cracks needed to cover the entire area. It is simply the most economical way for the stress to relieve itself across a vast, uniform plane. This is not a conscious choice, but a fundamental law of physics playing out in solidifying rock. The result is a landscape of hexagons, a testament to nature's relentless drive toward efficiency. You can see this exact same principle at work in other places. Look at the wax honeycomb built by bees. The hexagonal cells allow the hive to store the maximum amount of honey using the least amount of precious wax. Or examine the pattern of cracks in dried mud. While often more chaotic, you will still find a clear dominance of hexagons and other polygons trying to form. From the microscopic scale of certain cell membranes to the grand scale of the giant's causeway, this pattern emerges again and again whenever tension is released across a contracting surface. It is a universal signature, a hidden rule of our world made visible in stone. What does this tell us? It reveals that the order we see is not random design, but the inevitable outcome of physical laws. The causeway's beauty is not an accident, it is a direct expression of energy minimization. A frozen moment of the universe solving a problem in the most elegant way possible. This geometric rule is not unique to the coast of Ireland. Nature has been practicing this same art form in volcanic landscapes across the globe. Just across the sea on the Scottish island of Staffa lies Fingal's cave. Its entrance is a breathtaking colonnade of towering basalt columns, so perfectly hexagonal they appear carved by a divine hand. This is the other end of the Finn McCool legend, the Scottish side of the giant's mythical bridge. The geological reality is just as compelling. Both Fingal's cave and the giant's causeway were born from the very same ancient lava flow, a single geological event that connected these two lands long before any legend was born. The stone is identical, the process was identical, and the resulting beauty is a mirror image separated only by the sea. Travel to the Sierra Nevada mountains in California and you will find the Devil's Postpile. Here the columns are just as long and elegant, but they are often pentagons, and their tops are weathered into a surface that looks like a tiled floor. The key difference here was the size of the lava flow. It was smaller and shallower than the vast Antrim Plateau, which influenced the cooling rate and the resulting joint patterns. Yet the same fundamental physics were at work, creating order from a sea of molten chaos. In the dramatic landscapes of Iceland, the waterfall known as Svartifoss plummets over a sheer cliff of black columnar basalt. The columns here are darker and more slender, often looking like a stack of organ pipes or the pages of a massive book. Iceland is a land still being shaped by volcanic fire, and Svartifoss showcases how columnar jointing can create breathtaking scenery in a completely different environment. The lava that formed it was of a slightly different chemical composition, and it cooled under different climatic conditions, proving the versatility of this natural process. Each of these sites tells the same core story of cooling and contraction, yet each has its own unique character. The chemistry of the lava, the depth of the flow, the speed at which it cooled, all of these factors are variables that nature adjusts, resulting in a world of astonishing variety. From the colossal hexagons of Ireland to the slender pillars of Iceland, we see a single set of physical laws expressing itself in countless beautiful ways. Does this global family of stone formations make our own world feel smaller, or somehow even more vast and wondrous? The very same volcanic fissure that gave us the Giant's Causeway also carved a cathedral from stone across the sea. On the Scottish Isle of Staffa, the entrance to Fingal's cave is a breathtaking colonnade of towering basalt columns, their perfect hexagonal forms rising from the water like the pillars of a sunken palace. Geologically, these two wonders are twins, born from a single monumental event. that vast lava flow which blanketed Antrim 50 to 60 million years ago did not stop at the coast. It surged onward, filling a river valley that lay between the ancient landmasses, its fiery path creating a continuous geological layer that today connects Northern Ireland to Scotland beneath the churning waves of the North Channel. The science reveals a deep and tangible bridge, a real connection that existed long before any human set foot on either shore. It is an incredible coincidence that feels like something more. The legend of Finn McCool and his Scottish rival Benandina did not emerge from a vacuum. It was a story crafted by people who could see no other explanation for the matching stonework on two separate shores. How could identical columns appear in both Ireland and Scotland without some colossal, intentional effort? The myth provided the motive for a phenomenon that observation alone could not decipher. So the story of the two giants is not a mere fantasy laid over the truth. It is a profound human interpretation of a real geological link. The causeway and the cave are two halves of a single whole, a fact that science confirms and that legend personifies. This beautiful convergence makes you wonder if our oldest stories are sometimes closer to the truth than we realize, not in their literal details, but in their intuitive grasp of a connected world. Yet for all its elegance, the slow cooling theory has not gone completely unchallenged. Over the years, alternative ideas have emerged from the scientific fringe, each attempting to solve a piece of the puzzle in a different way. One persistent notion suggests that rapid cooling, not slow cooling, was the true artist. Proponents of this idea point to the possibility of water. Imagine that vast lake of lava suddenly inundated by a deluge of seawater or heavy rain. The dramatic temperature shock, they argue, could have caused the rock to fracture instantly into neat columns. It is an appealingly dramatic image, a sizzling cataclysm of steam and cracking stone. But the evidence in the rock itself tells a different story. If the lava had cooled rapidly, the resulting basalt would have a much finer grain, almost like glass. The columns at the Giant's Causeway, however, are made of crystalline basalt with visible mineral grains that could only have formed during a long, patient cooling process, giving the crystals time to grow. A quick chill would have frozen the rock in a more amorphous state. Furthermore, rapid cooling tends to create a chaotic, blocky rubble, not the deep, uniform columns we see. The sheer depth and perfection of the causeway's pillars stand as a silent rebuttal to the idea of a sudden freeze. Another line of inquiry has focused on the lava's unique chemical signature. Could a specific, rare mineral cocktail be the secret ingredient? Some researchers have delved into the precise ratios of elements like iron, magnesium, and silica, searching for a formula that would make basalt predisposed to crack into perfect hexagons. While the composition is indeed crucial, as we saw with the fluid tholeiitic basalt, these investigations have largely reinforced the standard model rather than overturned it. The chemical makeup created the ideal conditions for slow, even cooling and uniform contraction. It was the enabler of the process, not a magical geometric trigger in itself. So why does the thermal contraction model remain the reigning champion? Its strength lies in its predictive power and its universal application. It is not just a story that fits the Giant's Causeway. It is a principle that correctly forecasts the appearance of columnar jointing in other lava flows around the world, from the massive cliffs of Devil's Tower in Wyoming to the intricate colonnades of Iceland. The model provides a coherent, step-by-step narrative that aligns perfectly with the physical evidence locked in the stone, the size of the mineral crystals, and the incredible depth of the fracture patterns. These alternative theories, while creative, often explain one aspect while creating new problems elsewhere. They are like trying to force a single piece into a puzzle where it does not quite fit. The standard model, in contrast, shows how all the pieces, the chemistry, the depth, the slow loss of heat, lock together into a single, elegant picture. It demonstrates that sometimes the simplest explanation, governed by the most fundamental laws of physics, is the one that holds the most profound truth. What does this long scientific debate reveal? It shows that our understanding of the natural world is not set in stone. It is a living process of questioning, testing, and refining until only the most resilient ideas remain. While scientific debate raged in lecture halls, a different kind of discovery was unfolding on the Antrim coast. The world outside of Ireland was about to learn of this geological marvel, transforming it from a local legend into an international sensation. This shift began not with a geologist but with an aristocrat and a sketch. In the 1780s, Frederick Hervey, the Earl of Bristol and the Bishop of Derry, was a man of immense wealth and eclectic taste, renowned for his grand tours across Europe. When he first laid eyes on the Giant's Causeway, he recognized its potential not just as a curiosity, but as a destination. He commissioned the first proper artistic representations of the site, sending artists to capture its strange forms. These sketches and watercolors were his marketing tools, circulated among the elite circles of London and Dublin. They presented the Causeway not as a confusing scientific specimen, but as a spectacle of sublime nature, a place of awe that could rival any Roman ruin or Italian vista. The bishop had effectively put the Giant's Causeway on the map for the traveling class, creating a new kind of pilgrimage for those seeking the extraordinary. This new fame coincided perfectly with the rising tide of the Romantic movement. The 18th century was giving way to the 19th, and a new cultural sensibility was taking hold. Romanticism rejected cold rationality and celebrated raw, untamed emotion. It found its muse in wild landscapes that evoked feelings of wonder, terror, and the sublime. The Giant's Causeway was the perfect embodiment of these ideals. Here was a place that looked utterly unnatural, almost alien, yet was a pure product of the natural world. Its geometric perfection felt both rational and wildly chaotic, a contradiction that thrilled the romantic soul. Travelers no longer came just to see an oddity, they came to have an experience, to feel small in the face of a power greater than themselves. They followed in the bishop's footsteps, braving the rough journey to the northern coast, their minds primed by poetry and art to see not just stones, but a cathedral built by the earth itself. Among these early pilgrims was the novelist William Makepeace Thackeray. He visited in the 1840s, and his writings capture the sheer sensory overload of the place. He did not describe it with dry, scientific terms. Instead, he wrote of being utterly confounded and overwhelmed. He struggled to find words adequate for the spectacle, calling the Causeway a strange, terrible, bewildering sight. For Thackeray and his contemporaries, the beauty of the place was inextricably linked to its strangeness. It was this very unnaturalness that made it so profoundly moving. The Causeway challenged their perception of what nature was capable of, existing in a thrilling space between order and chaos. His published accounts, filled with this palpable sense of awe, served as a powerful review, enticing even more visitors to make the journey. They came on horseback, in carriages, and on foot, all seeking to witness with their own eyes the truth that was stranger than any fiction. The local economy adapted, with inns springing up and guides offering their services, turning a geological wonder into a cornerstone of Irish tourism. The stones, silent for millions of years, now found themselves at the center of a new human story, one of exploration, art, and the enduring desire to stand in the presence of the sublime. Susanna Drury's brush transformed the Causeway into a global icon. In the 1740s, long before photography, this Irish artist spent months on the rugged coast, meticulously capturing the bizarre geometry of the stones in two monumental paintings. Her work was not just a depiction, it was a revelation. She presented the Causeway with a startling clarity, rendering the interlocking columns and the wild sea with such precision that viewers felt they were standing on the cliffs themselves. The impact was immediate and profound. Her paintings were engraved and printed, and copies spread across Europe like geological postcards. They offered the world its first clear, accessible view of this impossible landscape, winning a top prize from the Dublin Society and capturing the imagination of an entire continent. For the first time, people in London and Paris could study the Causeway's forms without ever leaving their salons, fueling both scientific debate and public fascination. Drury's art did more than document. It framed the natural wonder as a subject worthy of intense, detailed observation, bridging the worlds of empirical science and aesthetic appreciation. Writers soon followed, wielding prose as their paintbrush. The Causeway became a powerful symbol in the literary imagination, a ready-made stage for exploring the concept of the sublime. This was the idea that nature could evoke a thrilling mixture of awe and terror, a beauty so vast and powerful it overwhelmed the senses. For romantic poets and novelists, the Causeway was a perfect muse. Its mathematical order hinted at a divine plan, while its volcanic origin spoke of primal, chaotic forces. It was a contradiction that writers loved, a place where reason and wild emotion collided. William Wordsworth, upon visiting, described the scene as a place where nature, with a mind unlike the human, had worked its will. He saw the columns not as mere rock, but as a testament to a non-human intelligence, a force that operated on a scale and with a logic beyond human comprehension. The Causeway became a character in its own right, a brooding, ancient presence in poems and travel narratives that challenged the very idea of a tame, orderly world. This artistic and literary celebration marked a profound shift in how humanity related to the wild. The stones were no longer just the stuff of local myth or scientific curiosity. They were now an emblem of the sublime. People began to travel to the Antrim coast not to solve a puzzle, but to have an experience. They came with Drury's engravings in their minds and Wordsworth's verses on their lips, seeking to feel that same overwhelming awe for themselves. They wanted to trace the hexagonal steps with their own hands, to hear the Atlantic crash against the pillars, and to stand in a place that made them feel wonderfully, terrifyingly small. The Causeway taught a generation that nature's greatest wonders were not just to be understood, but to be felt. This emotional connection, forged by artists and writers, ensured the Giant's Causeway would be protected not as a mere resource, but as a treasure of the human spirit. How does a place move from being seen to being felt, and why does that emotional resonance ensure its survival for generations to come? That emotional connection, forged by artists and poets, demanded a formal promise of protection. In 1986, the Giant's Causeway received the highest honor a place on Earth can achieve. It was inscribed as a UNESCO World Heritage Site, a title reserved for locations of outstanding universal value to all humanity. This was not merely an award, it was a global declaration that these stones belonged to everyone. To earn this status, the Causeway had to meet two strict criteria. It was recognized as a superlative natural phenomenon, a masterpiece of the Earth's creative forces. Its columnar jointing was held up as the most perfect and extensive example of its kind anywhere in the world. But its value was not purely geological. UNESCO also acknowledged its deep cultural significance, its profound influence on artistic and literary movements, and its powerful role in the development of Earth science. This dual recognition cemented the idea that the Causeway story is not one of nature or culture, but a seamless intertwining of both. The scientific mystery and the human response to it are inseparable parts of its identity. This designation fundamentally changed how the site is managed. It brought with it a rigorous management plan, a binding commitment to balance public access with long-term preservation. Visitor facilities were redesigned to minimize their footprint on the landscape. Scientific monitoring became continuous, tracking everything from erosion rates to the impact of foot traffic on the ancient basalt. Every decision, from pathway maintenance to educational signage, is now made with the primary goal of safeguarding the site's integrity for future generations. The UNESCO status acts as a shield, ensuring that the wonder which baffled scientists and inspired poets will not be compromised by short-term interests. It has also projected the giant's Causeway onto a global stage, transforming it from a national treasure into a planetary icon. The UNESCO emblem is a universal signal, telling travelers from every corner of the world that here is a place of profound importance. This global recognition fuels a sustainable tourism economy, providing the resources necessary for its ongoing care while instilling a sense of shared responsibility in every visitor who walks its stones. We are no longer just observers of this landscape, we have become its collective guardians, entrusted with a piece of the Earth's deepest history and our own human story. What does it mean to be a steward of such a place, and how does that responsibility shape our relationship with the natural world? Modern geology has moved beyond hammers and sketches, now employing tools that feel like something from science fiction to decode the Causeway's final secrets. Radiometric dating is our ultimate time machine, allowing scientists to pinpoint the Causeway's birth with astonishing accuracy. This technique does not measure years directly, but instead analyzes the slow, predictable decay of radioactive elements locked within the basalt when it first cooled from lava into solid rock. By measuring the precise ratio between a parent element, like potassium, and its stable daughter element, argon, scientists can calculate the exact moment the rock solidified. The results are definitive. The giant's Causeway was formed between 55 and 60 million years ago, placing its creation firmly in the Paleogene period, a time when ancient mammals were just beginning their rise after the extinction of the dinosaurs. This precise age is not just a number, it is the foundational piece of the puzzle, confirming the volcanic origin and giving us a clear window into a specific, fiery chapter of Earth's deep history. Geochemical analysis acts as the Causeway's DNA test, revealing the unique recipe of the lava that created it. Scientists use powerful instruments to vaporize tiny slivers of the basalt, separating its elements to be counted and identified. This process reveals the precise chemical signature of the rock, the exact percentages of silica, iron, magnesium, and trace elements that defined its character. This data confirms it was indeed the fluid tholeiitic basalt we discussed, but it goes much further. By comparing this chemical fingerprint to other volcanic rocks across the region, geologists can trace the Causeway's lava back to its specific volcanic fissure, mapping the exact flow paths of these ancient floods. It reveals that the same magma source fed the identical columns at Fingal's cave in Scotland, providing concrete scientific proof of the geological bridge that the legend of Finn McCool only hinted at. The chemistry tells a story of source and flow, confirming that the conditions were not just right, but uniquely perfect for the creation of this geometric marvel. Perhaps the most visually stunning modern tool is three-dimensional laser scanning. Tripod-mounted scanners now project millions of laser points across the Causeway's surface, capturing every crack, curve, and column in a dense point cloud of data. This creates a digital twin of the entire site, a perfect three-dimensional model that can be rotated, measured, and analyzed from any computer in the world. This technology provides a level of precision that was once unimaginable. Researchers can now measure the exact angles between columns across the entire formation, analyzing the stress patterns in a way that was impossible with the naked eye. They can calculate the volume of individual pillars and map the subtle variations in the cooling fractures from the tops of the columns down to their submerged bases. This immense dataset allows scientists to run sophisticated computer simulations, testing the slow cooling theory against a perfect digital replica. They can input variables like lava depth and cooling rate to see if their models produce the same fracture patterns we see in reality. This process continuously refines our understanding, confirming that the slow, steady loss of heat from a deep, homogeneous pool of lava is the only process that can account for the Causeway's breathtaking scale and perfection. These tools do not replace the old theories, they elevate them, providing a level of confirmation so detailed it feels like we are witnessing the formation itself. What other secrets might these digital ghosts of stone reveal as we continue to listen to their ancient story? The same physical laws that forged these stones now shape the path of every visitor who walks upon them. The journey begins at a visitor center designed to echo the Causeway's own geometry, its angular roof a modern homage to the basalt columns. Inside, the ancient rivalry between science and legend comes to life through interactive displays. You can trace the path of that 50-million-year-old lava flow on a glowing map, then turn a page in a digital book to hear the tale of Fingal shouted over the roar of a virtual sea. This modern gateway does not force you to choose between the two stories. Instead, it frames them as different languages trying to describe the same profound wonder. It prepares you not just with facts, but with a sense of context so that when you finally step outside, you are carrying both the weight of deep time and the spark of human imagination. The path from the center winds down toward the coast, building anticipation with every step. Then the landscape opens up and there it is. It is one thing to see a picture and another entirely to stand at the edge of this sprawling stone pavement. The first sensation is one of sheer scale. 40,000 columns march into the ocean, a vastness that photographs can never truly capture. You step down onto the first hexagonal pillar. The surface is uneven, worn smooth in places by millions of footsteps and millions of storms, yet still rugged and sharp in others. Your feet tell you a story your eyes cannot, feeling the subtle tilt of each column, the gaps between them, the solid, unyielding reality of the stone. You hop from one hexagon to the next, following a natural pathway that seems to lead you deeper into the puzzle. The Atlantic wind is a constant presence, whipping across the bay, carrying the salty taste of the sea. Then you hear it, the low, thunderous boom of a wave crashing against the far end of the causeway. A curtain of white spray erupts into the air, and seconds later, a fine, cool mist kisses your face. This is not a static monument, it is a dynamic battleground where the ancient power of the earth meets the relentless energy of the ocean. You find a perch on a tall column, its top a perfect, if slightly uneven, seat. From here, you can watch the waves roll in, each one exploding against the geometric edges of the basalt, the water swirling and foaming in the narrow channels between the pillars. It is a hypnotic display of raw force. The ocean is slowly, patiently reclaiming the causeway, grain by grain. You are sitting on a moment of geological time, witnessing the slow-motion dance of creation and erosion. Children scramble over the lower columns, their laughter carried on the wind, while others stand in quiet contemplation, trying to absorb the immensity of it all. This is the magic of the place, its ability to hold both playful exploration and deep reverence within the same stretch of coast. To walk here is to feel a direct physical connection to a force that shaped the world long before we arrived, a reminder that we are merely temporary guests in a story written in stone and sea. That ancient drama of stone and sea has not faded with the ages. It has found a powerful new stage in modern media, where the giant's causeway continues to command the screen and inspire the artist's hand. Its striking, otherworldly appearance makes it a natural choice for filmmakers seeking a landscape that feels both epic and alien. It served as a key location for the television series Game of Thrones, representing the Iron Islands. When characters stood upon those hexagonal stones, swearing oaths and plotting rebellion, the causeway provided a raw, formidable backdrop that whispered of ancient power and unyielding strength. The stones themselves became a character, their geometric perfection echoing the harsh, rigid codes of honor that defined the Ironborn culture. This was not just a pretty place to film, it was a deliberate choice to root a fictional world in a real place of profound and palpable history. The causeway's ability to evoke a sense of mythic scale makes it a magnet for stories that operate on a grand canvas. It has appeared in music videos, its stark beauty amplifying themes of longing and journey. It graces the pages of contemporary fantasy novels, where authors describe their own fictional wonders by simply invoking its name. The Causeway has even marched into the digital realm, its distinctive form inspiring level designers in video games who create virtual worlds of primordial mystery. When a player traverses a landscape of geometric pillars in a game, they are walking in the footsteps of a real wonder, whether they know it or not. Why does this place resonate so deeply with our modern myth-making? It is because the Causeway is a ready-made symbol. Its very existence feels like a plot point in the Earth's own story. For a creator, it offers a shortcut to the sublime, a location that requires little embellishment to feel magical and immense. You do not need to build a fantastical set when nature has already provided one that surpasses imagination. This ongoing cultural presence does more than just promote tourism. It performs a vital act of translation. It takes a complex geological phenomenon and translates it into the universal language of story and emotion. A teenager who has never heard of columnar jointing might see the Causeway in a film and feel a spark of awe. That spark might lead to a question, which might lead to a search, which might lead to a lifelong passion for geology or history. The Causeway, through its countless appearances in our shared culture, becomes a gateway. It reminds us that the lines we draw between science and art, between nature and story, are often illusions. The same primal force that compels a scientist to study the cooling rate of basalt compels a filmmaker to frame a shot against those perfect pillars. Both are seeking to capture a piece of the same profound truth, a truth written in stone 60 million years ago and still being read in countless new ways today. What stories will this place tell in the next 100 years, and what new creators will it inspire to look closer at the world beneath their feet? But this global fame comes with a heavy price. The very footsteps that seek connection with this ancient wonder also threaten its delicate surface. With over 1 million visitors each year, the cumulative impact is a constant concern. Each shoe scuffs the basalt, slowly polishing away the rough, natural texture of the columns. The pressure of countless feet can widen the cracks between the pillars, accelerating the natural process of erosion. It is a silent, gradual wear that happens one visitor at a time, a human-induced weathering that adds to the relentless work of the Atlantic weather. The Causeway endures a constant assault from wind, rain, and salt spray. The sea that pounds its edges is not just a dramatic backdrop, it is a powerful geological agent. Storm surges, growing more frequent and intense with climate change, hurl massive waves against the columns, testing their ancient bonds. The freeze-thaw cycle is another silent sculptor. Water seeps into the smallest fractures, and when winter comes, it freezes. As water turns to ice, it expands with immense force, acting like a wedge to pry the stone apart from within. This natural process, which has shaped the Causeway for millennia, is now being supercharged by more extreme weather patterns, threatening to break down the geometric perfection faster than ever before. The most insidious threat, however, is one that cannot be seen by the naked eye. Climate change and rising sea levels present a long-term danger to the entire coastline. A higher sea level means that storm waves can reach farther inland, attacking the base of the cliffs that support the Causeway and undermining its very foundation. Increased rainfall and more acidic oceans, driven by higher carbon dioxide levels, can also chemically weaken the basalt over time, making it more susceptible to all other forms of erosion. The Causeway has survived for 50 million years, but the unprecedented speed of modern environmental change poses a challenge it has never faced before. Managing these intersecting threats requires a careful and constant balancing act. How do you allow people to experience a treasure without loving it to death? The answer lies in proactive and often invisible stewardship. Pathways are carefully designed to channel visitor flow away from the most fragile areas. Regular scientific monitoring tracks erosion rates down to the millimeter, allowing for early intervention. The visitor numbers themselves are managed to prevent overcrowding, especially during peak seasons. Education is a critical tool, with guides and signage gently reminding everyone that they are walking on an irreplaceable piece of the planet's history. The goal is not to keep people away, but to foster a sense of shared guardianship. Every visitor becomes part of the solution, treading lightly and leaving nothing behind but their awe. This is the modern covenant for a World Heritage Site, a promise to ensure that the giant stepping stones remain for the next million footsteps and for the million after that. What legacy of preservation will we leave for the giants of the future? Zooming into the very fabric of the stone reveals a hidden universe. The dark gray basalt is not a uniform mass, but a dense tapestry of interlocking crystals, each one a tiny time capsule. To truly understand the Causeway's patient creation, we must look at the minerals themselves, specifically plagioclase, feldspar, and pyroxene. These are the primary ingredients, the fundamental building blocks that crystallized from the molten soup. Plagioclase feldspar forms slender, lath-shaped crystals, often peeking out with a slight sheen. Pyroxene appears as darker, blockier grains, filling the spaces between. This specific mineral recipe is crucial as it dictated how the lava behaved, its melting point, and its ultimate strength. But the real story is not just in their presence, it is in their size and their relationship to one another. The crystals in the Causeway's basalt are remarkably small, almost too fine to see with the naked eye. This seemingly minor detail is one of the most important clues geologists have. The size of a crystal is a direct record of time. In a rapidly cooling lava, atoms do not have time to arrange themselves into large, orderly crystals. The result is a volcanic glass, like obsidian, with no crystalline structure at all. Conversely, in a magma chamber that cools over thousands of years deep underground, crystals grow to a massive size, like the sparkling points in a granite countertop. The Causeway's basalt sits perfectly in the middle. Its fine-grained, yet distinctly crystalline texture is the unmistakable signature of a moderate cooling rate. It tells us the lava did not chill in a panic, nor did it slumber for ages. It cooled steadily over decades or perhaps even centuries, allowing these tiny, intricate crystals of feldspar and pyroxene to nucleate and grow in a dense, strong matrix. This is the final, microscopic confirmation of the slow cooling theory. The entire lava flow acted like a single, massive casting, with the heat escaping so evenly that the resulting rock has an almost identical fine-grained texture from the top of the columns to their base. By analyzing thin slivers of rock under powerful microscopes, scientists can even detect subtle variations in crystal size and orientation. These minuscule gradients map the flow of heat with incredible precision, revealing exactly how the temperature dropped from the cool surface downward into the still molten heart of the flow. Each tiny crystal of feldspar is a frozen moment in that great, slow chill, a testament to the patient physics that transformed a lake of fire into a masterpiece of geometry. The columns we walk upon are merely the surface expression of a far grander story. To understand the true scale of this event, we must pull our gaze back from the shoreline and look at the entire region. The Giant's Causeway is a spectacular detail, but it is just one small piece of a colossal geological structure known as the Antrim Lava Group. This is not a single layer of rock, it is a towering stack of multiple basaltic lava flows that built up over time, burying the ancient landscape beneath them. Imagine not a single eruption, but a series of them, each one flooding the land with liquid fire, then cooling, only to be covered by the next deluge millions of years later. This sequential layering created the Antrim Plateau, a vast, elevated tableland that dominates the geography of County Antrim. The Causeway represents just the top layer of this immense volcanic cake, the final chapter in a long saga of fire. The scale of this province is almost incomprehensible. At its thickest, the Antrim lava group is nearly 2,000 feet deep, a staggering accumulation of frozen lava that covers an area of over 3,000 square miles. This makes it one of the most extensive and significant volcanic provinces in all of Europe, a remnant of a time when this corner of the world was a hotspot of planetary activity. The individual flows that built this plateau vary in thickness and character, telling a story of different eruption styles and pauses. Some layers are dense and fine-grained, like the Causeway basalt, indicating deep, pooled lava that cooled slowly. Others are more vesicular, filled with the ghostly impressions of gas bubbles that were trapped as the rock solidified, hinting at more violent, frothy eruptions. Between some of these lava flows, scientists have even found thin layers of fossilized soil called paleosols. These ancient dirt layers are the smoking gun, the proof of quiet intervals that could last for hundreds of thousands of years. During these long pauses, the top of the most recent lava flow would slowly weather, and primitive plants would take root, establishing a fragile ecosystem on the barren rock. Then, without warning, the fissures would tear open again, and the next wave of molten basalt would pour forth, incinerating that fledgling world and sealing it beneath a new tomb of stone. This cycle of creation and destruction, repeated over millions of years, built the plateau layer by layer. So when you stand on the Giant's Causeway, you are not just standing on the result of one eruption. You are standing on the summit of a mountain range built not by uplift, but by accumulation, the final monument to an age of fire that shaped the very foundation of Northern Ireland. For all its geometric perfection, the Causeway is not a monotonous grid. Look closer and you will see the story is more complex. While most columns are hexagons, a significant number are pentagons, and you can even find some with 4, 7, or 8 sides. This variation is one of the small, lingering puzzles that keeps geologists debating. Why would the same physical process produce such a range? The prevailing theory suggests that small imperfections in the lava flow, tiny variations in its composition, or the presence of minuscule bubbles could have acted as nucleation points, subtly steering the propagating cracks and changing the angles at which they met. It is a reminder that nature, even at its most mathematically elegant, is never a perfect machine. Another active debate revolves around the ground beneath the ancient lava. The topography of the 50-million-year-old landscape, the hills and valleys over which the molten rock flowed, would have influenced the lava's depth and its cooling rate. A deeper pool in a valley would cool more slowly than a shallow sheet over a ridge, potentially creating variations in column thickness and length across the causeway. Pinpointing the exact contours of that lost landscape is a detective story in itself, a challenge of reconstructing a world that was buried in fire. The most profound unanswered question asks if thermal contraction was the only artist at work. Could other forces have contributed to the flawless fracturing? Some researchers point to the role of desiccation, the idea that as the lava solidified, it also lost water vapor and other volatiles, causing a different kind of shrinkage that may have worked in concert with thermal contraction. Others explore the complex physics of how the cracks actually propagated. Did they form all at once from the surface down, or did they initiate at multiple depths and link up? These are not challenges to the core theory, but refinements, an ongoing effort to understand the finer brushstrokes in this masterpiece of natural engineering. The Causeway, in its beautiful inconsistency, proves that a solved mystery can still hold deep and fascinating secrets. What other subtle clues are hidden within the angles of a pentagon, waiting for a curious mind to notice? These stones are a silent dialogue between two ways of knowing the world. They stand as a permanent bridge between the vibrant realm of human myth and the rigorous domain of scientific discovery. On one side, you have the fiery tale of Fingal, a story of pride and power that gave the landscape a soul. On the other, you have the slow, patient narrative of cooling lava, a story that gives the same landscape a history. The Causeway does not ask you to choose between them. Instead, it reveals that both are essential to our understanding, that the human need for story and the scientific pursuit of truth are not enemies, but two different languages describing the same profound mystery. This geological marvel is a testament to our planet's restless, dynamic history. It is a fossilized moment of pure creation, a reminder that the ground beneath our feet is not permanent, but was forged in unimaginable violence and shaped by patient, universal laws. The Causeway is a direct line to a time when the Earth itself was the only artist, painting with fire and ice on a canvas of deep time. Its endurance through 50 million years of wind and wave is a humbling lesson in planetary scale, challenging our own fleeting perception of the world. For Ireland, these columns are more than a tourist attraction. They are a cornerstone of cultural identity. They are a symbol of resilience and unique beauty, a natural monument that anchors the nation's sense of place. The legend of Finn McCool is woven into the very fabric of Irish folklore, a story told to children for generations. The Causeway is a point of immense pride, a piece of the homeland that is recognized and revered across the globe. It represents a connection to an ancient past, both geological and cultural, that continues to define the present. On a universal level, the Giant's Causeway has become an enduring icon of natural wonder. It is a place that fundamentally challenges our perception of what is possible. Its geometric perfection feels so deliberate, so designed, that it forces us to reconsider the very boundary between order and chaos in the natural world. This is why it continues to inspire such a powerful sense of awe in every visitor. That feeling is more than just surprise. It is a profound emotional response to something that transcends everyday experience. It is the feeling of being small in a universe that is vast, ancient, and breathtakingly beautiful. To stand there is to feel a connection to something much larger than yourself, a reminder that the world is still full of wonders that defy easy explanation. How does a place become more than the sum of its stones, and what does our enduring awe for it say about our own place in the grand story of the Earth? Laboratory experiments have brought this ancient process vividly to life. Scientists could not travel back 60 million years, so they did the next best thing. They recreated the conditions in their labs. Using simple, everyday materials, they have proven the physics behind the Causeway's creation beyond any doubt. One of the most revealing experiments involves a slurry of cornstarch and water. Researchers pour this thick, wet mixture into a tray and then gently heat it from below. As the water slowly evaporates, the starch slurry dries out and contracts. Almost like magic, a network of cracks begins to form on the surface. These are not random fractures. They quickly organize themselves into a familiar honeycomb pattern of polygons dominated by hexagons. The experiment is a miniature, speeded-up version of the Giant's Causeway's formation. The drying starch acts exactly like the cooling basalt, shrinking and cracking to relieve internal stress in the most energy-efficient way possible. This simple kitchen science demonstration provides stunning visual proof that the same universal laws govern both a pan of drying goo and a 50-million-year-old lava flow. Another powerful experiment uses wet clay. A thick layer of clay is spread out and left to dry in the sun. As the water within it evaporates, the clay contracts and pulls apart. You have likely seen this yourself in a dried-up puddle. But on a larger, more controlled scale, the resulting crack patterns are unmistakably geometric. Researchers can even manipulate the results by changing the variables. They can alter the thickness of the clay layer, the rate of drying, or the composition of the clay itself. A thick layer that dries slowly will produce deep, well-defined columns, just like the Causeway's pillars. A thin layer that dries quickly creates only a shallow, chaotic crust of small, irregular pieces. These experiments are not just replicating a pattern, they are testing the theory of thermal contraction under controlled conditions. Every time the clay or starch cracks into hexagons, it validates the scientific narrative of the Causeway. The laboratory becomes a time machine, allowing us to witness in minutes a process that nature took centuries to complete. These tangible models bridge the gap between abstract theory and physical reality, giving us a profound appreciation for the predictable, beautiful laws that shape our world. The Atlantic will not cease its patient work. The same waves that draw millions of visitors will continue their slow, inexorable reclamation of the stone. Over the next 10,000 years, the relentless cycle of wind, water, and ice will gradually smooth the sharp edges of the hexagons, rounding them down like old teeth. The tallest columns will be undercut by storm surges, causing them to tumble into the sea one by one. The causeway will slowly retreat, its geometric pavement surrendering to the ocean, becoming a submerged reef that future generations might only know through our images and stories. This is the natural destiny of all coastlines, a beautiful, melancholic dance of creation and decay that has been underway for 50 million years, yet human hands are now part of this equation. The future of the causeway is not solely a story of natural erosion, but a test of our commitment to stewardship. Conservation science is advancing as quickly as the threats themselves. Researchers are now using three-dimensional models from laser scans to predict exactly which columns are most vulnerable to the next major storm. They can simulate wave action and erosion patterns with astonishing accuracy, allowing for preemptive reinforcement of cliff faces and the strategic placement of natural sea defenses. New, non-invasive techniques for strengthening the basalt are in development, including mineral-based solutions that can seep into the microscopic fractures and bind the stone from within, acting as a synthetic glue to slow the work of the freeze-thaw cycle. The goal is not to stop time, which is an impossible task, but to manage its effects, to ensure the causeway's grandeur endures for as many human generations as possible. This mission extends far beyond the coastline itself. Sustainable tourism is the crucial link between preservation and access. The future may see a managed reservation system, not to keep people away, but to guarantee every visitor has a profound and uncrowded experience while minimizing cumulative wear. Virtual reality tours crafted from those detailed scans could offer an immersive journey for those who cannot make the physical trip, or even a digital preview that prepares visitors to tread more lightly when they arrive. Education is the final, most powerful tool. The story told to schoolchildren is evolving from a simple legend or a dry geological fact into a unified narrative of wonder and responsibility. They learn that Finn McCool's bridge and the volcanic fissure are two sides of the same truth, and that their role is to become the next guardians of that truth. They are the future scientists who will develop new conservation methods, the future policymakers who will protect the site's integrity, and the future visitors who will carry the story forward. The Giant's Causeway will change, as all living landscapes must, but our collective promise is to ensure that its power to inspire awe and curiosity does not fade with the stone. What kind of ancestors will we be for the giants yet to come? Two vastly different stories, one of giants and one of geology, both lead us to the same breathtaking shore. The Giant's Causeway is a permanent monument to our dual need for wonder and understanding. It reminds us that our planet's history is written in a language of fire and force, a narrative of unimaginable violence giving way to patient mathematical perfection. We began with a legend of epic strength and rivalry, a tale that gave human meaning to an impossible landscape. We ended with a scientific saga of a deep lake of lava, cooling for centuries until it cracked itself into the geometric masterpiece we walk upon today. Both stories, in their own way, are true. One speaks to the soul of a place, the other to its substance. One is a story of character, the other a story of chemistry and physics. The Causeway does not ask us to choose between myth and science, but to see them as partners in a greater quest for meaning. This bridge of stone is a magnificent example of nature's own artistry, born from planetary fire and shaped by the unbreakable laws of our universe. It stands as a testament to the fact that the world's greatest wonders often lie at the intersection of what we feel and what we can prove. So we turn the question over to you. What does the Giant's Causeway make you wonder about our world? Share your own thoughts on this enduring mystery in the comments below, and tell us which of the Earth's other magnificent puzzles would you like to see us explore next.